Let's start with our favorite equation, Ax equal to b, our favorite matrix that is of size m rows and n columns. We had the column picture of matrix equations or linear equations. That is kind of like working with the vector space defined by the columns of A. The solution in that picture, in that way of looking at the system of linear equations, be that linear combination of the columns of A that gives you B, because Ax is a linear combination of the columns of A weighted by the components of X. And if you can find the right components so that you get B, then that would be the solution. So once again, Ax is the same as the columns of A sub I, n of them, because there are n columns, n unknowns, and weighted by the corresponding unknowns. And if you can find the right values for xi, that I get b, then I'm done. That is a solution. If you're working with row picture, each row in Ax equal to b stands for an equation, and these equations in the coordinate space will form something like lines or planes or some shapes, hyperplanes. And the right solution would be the intersection of all these shapes. There are two lines. If there is an intersection, that would be the right solution. There are three planes, and then there is an intersection, all three planes cutting each other at a point. That would be the solution. Point or set of points, because if there are two planes, the intersection might be a line, so that's the set of points. Common to all the equations or all the shapes will be the solution. So that is the row picture, but this is not the view we will take anymore. We have graduated from that view to the column picture, and that's the picture that we will work with starting today, actually starting last week. Now, we also looked at spans and linear combinations and subspaces. So let's kind of review span. If you have n vectors, let me call them ai again. Each one has m components, so they belong to Rm. If I take all possible linear combinations of these n vectors, that is called a span. That's the definition of the span. So instead of saying set of all possible linear combinations, I can just span of ai, n vectors ai. And so n, of course, is a number, is a count, so it has to be some positive number, integer. And the span, the official definition, mathematical definition, would be the set, that is what the curly brackets indicate, the set of all vectors x such that x is a linear combination of vectors of the type ai, and there are n of them, there are n vectors, so there are n numbers that I have to use. I'm looking for all possible linear combinations, so I use any number. I keep changing the numbers. How many vectors do I have in the span of n vectors of the type ai, m-dimensional vector? It's an infinite number, because I can take any possible value of si. Any span will have an infinite number of vectors. And suppose I start with just one ai, just call it a. All the scale versions of that vector will be in the span, so it's a line of vectors. That's infinite number of vectors again. So all spans will have infinite number of vectors. Now, subspace is like a span of a number of vectors is actually a subspace, because these are linear combinations. So if I take any vector in that span, and if I want to scale it by a number, I'll get another vector which also will be in the span. If I take two vectors and add them, that also will be in the span, because span contains all possible linear combinations. So a span is actually a subspace, and that's a practical definition of a subspace. So let me call that subspace C. Now each vector ai has m components, so the span will be a subspace of Rm. So the space is actually a subspace of Rm. So the containing space is Rm. So I'm just calling and using the symbol C, calligraphic symbol C. Now suppose among the n vectors that I started from, n ai vectors, suppose only R of them are linearly independent. Then that will form a basis for the span, because you're looking for the minimal set of vectors that will span the subspace. That is the definition of the basis, and the linearly independent ones will be the right ones to choose. The subspace will have R linearly independent vectors as the basis, and the cardinality of the basis, number of elements in the basis, which is R, that will be the dimension of that space. I'm trying not to say this, but as you can see, basically I'm thinking of a matrix and its columns ai, the matrix of size m rows and n columns, and with a rank R. R can never be greater than m, because if you have only m components, you cannot have more linearly independent vectors than the components, nor can it be more than n, because you have only n vectors. You cannot have more linearly independent vectors than the total number that you have. So there are only R vectors among the n vectors that are linearly independent. So R, as you know, is less than or equal to the minimum of m, the dimensionality of each vector, and n, the number of those vectors. Now, if m is if the number of linearly independent vectors is the same as the number of elements of the vector, then subspace is actually not subset of Rm, it's actually all of Rm. I have a matrix A, it's got n columns standing side by side. Each one has m components because its matrix is of size m rows and n columns. And the column space is defined. The column space of A is a set of linear combinations of the columns of A, all possible linear combinations. The set of all possible linear combinations is a span of the columns of A. That is the column space. It has to be a subset Rm because each column vector has m components. So it can be a proper subset or it can be all of Rm. Now, how do you specify it? Suppose I ask you to compute the column space. There are three entities I'm looking for. I'm looking for the continuous space. So you have to say the column space is a subset Rm or is equal to Rm. And I want to know the dimension, which will be the rank of the matrix. And then you have to give me the basis vectors. How many of them will you have? Same as R. The linearly independent vectors that will define the space, that will span the space. Remember, if you have n vectors, those vectors will span a space, but you don't need all n in most cases. You need only the linearly independent ones. Just because you have more doesn't mean that you cannot create a span. For instance, suppose I have a vector 1, 0, and if I take all possible linear combinations or the span of this vector, that will be all of x-axis or infinite number of vectors along the x-axis. Now suppose I have a few more vectors 1, 0, 5, 0, 2, 0, etc. in a matrix. Its column space is a span of all those columns, but it is the same as the span of just one. Well, first of all, it's a span of the three vectors. Let me call them A1, A2, and A3. But it's the same as the span of A1 because other vectors are just scalar multiples in this case of the first vector. So there's no harm in specifying more vectors that you need when you say you want to span, but there is no value in it either. If I'm looking for the basis, then you cannot specify all three vectors as in the example I just showed you. You have to specify only one. Any one of them will do, but the first one is probably the best one, referring to the example that I just showed you. Now, how many linearly independent vectors are there in A? That would be the rank of A. There is a definition. The linearly independent columns of A would be the column rank, which is the same as the row rank. So it is the rank of A. What's the dimension of each one of these vectors, each one of the column vectors? That would be the number of elements in the vector. That would be the number of rows of A. So that would be M. What's a good basis? This is a tricky question. What's a good basis? How do you find a good basis? What you would do is to run Gauss elimination, get its row echelon form. So then you will have pivots somewhere. And you will take the pivot columns, but not in the REF, not in the row echelon form, but in the original matrix. That will give you the linearly independent columns. So the pivot columns of the original matrix would be a good basis. So this is all I'm just telling you without really explaining it too much because you will see examples very soon. Now let's look at the significance of the column space. Now, starting from the column picture of linear equations, system of linear equations, we know that Ax equal to B, solving Ax equal to B is the same as looking for right linear combination of the columns of A such that you get B. That is the process of solving in the column picture. Okay, so we will be basically looking for xi's so that we can take the right linear combination to get the right hand side. But we also know that the column space is the span of the columns of A. So it's the collection of all possible linear combinations. B is not in that column space. Obviously, you cannot find the linear combination because it's not a possible linear combination. So the solution is possible if and only if B is a member of the column space. So that is the significance of the column space. Now, another thing that you might want to keep in mind is that if you do elementary column operations, what are elementary column operations? Those would be like, so it's basically like taking linear combinations of the columns. All those linear combinations will still be in the column space because column space contains all possible linear combinations. In other words, elementary column operations do not change the column space of a matrix. And if you remember, Gram-Schmidt basically was a set of elementary column operations to get to the orthonormal version of a matrix. So the column space of the original matrix and the column space of the orthonormal version of it are the same. They may be situations, some algorithms where you want matrix that is orthonormal but with the same column space. But on the other hand, elementary row operations do change the column space because you're actually messing with elements. What will not change in that case will be some other space which we might call the row space, because you're taking linear combinations of rows. And if you think of all possible linear combinations of the rows of a matrix as a space, that would be the row space. But